Okay, everyone, this is going to be your Section 2 notes for forces, and today we're going to talk about force diagrams and net force. So first we're going to talk about force diagrams, and force diagrams are used to show all of the forces on a receiver, not just one like force arrows. And to represent the receiver in a force diagram, there is a dot in the very middle of the diagram. So I'm going to show you what a few look like. So to show you an example of a force diagram, we need the picture of the receiver that we're going to be showing all of the forces on. So I've chosen this little flamingo statue to be our receiver. So when you draw a force diagram, the first thing that you need is a dot in the middle. So I'm going to go ahead and draw that. Then you need to go through your list of forces and figure out which ones are actually on the object. So if we go down through our list, we have gravity first, which gravity is on everything on Earth, so we can go ahead and add that to our force diagram. And in the force diagram, gravity is going to be the thing that is always pulling the object towards the Earth, pulling it down. So we would draw our arrow like this, and of course you have to label it. So force of gravity is on the statue, down in direction. So then the next thing on our list would be applied. There's nothing pushing or pulling this statue, so there would be no applied. Next one on our list is normal force. And since this statue is sitting on a tabletop or something, there is normal force. And since the tabletop is this direction, that means that normal force is going to be perpendicular to it or in this direction. So we're going to draw normal force going up like this and label it. And you see how I made my arrows approximately equal in length? That shows that this object is being both pushed and pulled in an equal amount, pulled by gravity and kind of held up by normal. So that means that it's not moving up or down, it's just sitting there. Our next one on the list is friction. Since the statue is not moving, there's no friction. Then the last one on our list is tension. And since there's no ropes, chains, or anything like that, there is no tension. So this is my force diagram for this picture. Easy as that. So this time I have a little bit more of a complex example to show you. This sled is going to be our receiver, and we're going to assume that it is in motion this time. So we're going to assume that the sled is being pulled. So the first thing that we need is our dot in the middle, and then go through your forces. First one is gravity, which of course there's gravity on the sled pulling it down. That's why it's sitting on the surface of the Earth. So there's gravity. Next one that we have is applied force. And based off of this picture, there is nothing pulling the sled as of right now. So there would be no applied. Then our next force on our list is going to be normal, which the sled is sitting on a surface. So it's sitting on a surface that's like this. So the normal force is going to be perpendicular. So straight up again. So we have normal and gravity kind of countering each other. And then next on our list would be friction, which we already decided that the sled is moving, and it would be moving to the right. So that means that our friction is going to be to the left. Okay. So the question is, what force is causing the sled to move? And you can see that the object touching the sled that's actually causing it to move is a rope. So that means that we have some tension. And tension is being caused kind of in this direction. And that tension has to be greater than the force of friction to show that there's some movement. So we're going to go ahead and put our tension arrow like that. So this would be our force diagram for the sled. Our last example force diagram is going to be for this owl sitting on the tree branch. And if our receiver is the owl, we can go ahead and draw our dot right here. And then go through your list. Does the bird have gravity on it? Yes, it does. That's how it's able to sit on the branch. And then, is there any applied force? No. The bird is not pushing. It's just simply got the force of gravity on it, holding it on the branch. And then next would be normal, which the bird is in contact with a surface under its feet. So there is going to be a normal force perpendicular to the branch like that. No friction because the bird is just sitting there. And no tension because there are no ropes, chains, or anything like that. So this is our force diagram for the bird sitting on the limb. And so force diagrams are pretty easy. Just go through your list and decide what is present and what is not. So now that we know what a force diagram is, we're going to go ahead and move on in the notes and talk about forces being vectors. And vectors include both magnitude and direction. And if you remember from last time, magnitude means strength. Because if you think about the magnitude of an earthquake, that's going to resemble its strength. So magnitude of a force talks about its strength. So anytime a force is represented, it has to be represented both as its magnitude and a direction of the force. So the question is, we know that we're supposed to say, or it's supposed to include information about magnitude when we draw a force arrow. And most of the time we can do that with the length of the arrow, but another way we can do it is actually showing with numbers the strength of the force. And so one way we can do that is to put the measurement of the force using the unit of force, which is the Newton, of course, named after the very famous scientist. Kind of came up with the rules for forces. So a force can be measured in the unit of newtons. So let me give you an example. So an example of forces as vectors, where we include the magnitude with an actual number, would be something like this right here. So we can get the information that an object is moved by 3 forces. And the first force that moves the object is a force of 10 newtons in the south direction. So if my object starts right here, normally you would have some sort of a grid to show you how big of an arrow to draw, but this is an example, so we'll kind of eyeball it. The first force that happens moves it 10 newtons south. So we can represent that with force arrows we're using as vectors. The second force that moves this object is going to be 40 newtons south, which means it's going to be much larger than the previous one. And we have to label it. So 40 newtons south is going to move the object yet again in the south direction. Then the third force that occurs is going to be the force of 15 newtons west. So the object is going to begin from its last position and move 15 newtons to the west. So this is a way to show forces as vectors. We use those force arrows. We're showing magnitude by writing the actual measurements of the forces, but also showing the length of the arrow, and then the direction that the arrow points is the direction of the actual force. So these are good examples of forces as vectors, something that includes both magnitude and direction. So now we're going to talk about something called net force, which can also be thought of as total force, so I kind of added that in there. And I've given you 3 scenarios here with these forces acting on these 3 boxes. So let's take a look at this first one. If I told you to tell me what is the total force on the first box, what would you say? And I bet most of you are saying, well, it's 20 newtons because they're both going in the same direction. So they're going to add together, which you're totally right. The total force is 20 newtons. And so that's exactly what you do. When forces are in the same direction, you simply add them together to get the total force. Makes total sense. And so in this situation, the box is actually going to move to the right. So this caused a change in position, a change in motion. Now, if I told you to look at the second box here and tell me the total force, what would you say? And I bet most of you are saying, well, it would be 5 newtons because the 15 is going to cancel out the 10 and still have 5 left over. Well, you're completely right again. Total force on this box, I just wrote that wrong, is going to be 5 newtons because the 15 does cancel out the 10 and there's 5 left over. So which direction is the box going to move now? Yep, it's going to move to the left. So again, you have a change in motion, and again, we can kind of sum this up over here to the right. When forces are in opposite directions, you subtract. Now, if we look at this last box here on the bottom, and I ask you to tell me total force, what would you say? I bet a lot of you are saying, well, it has to be 0 because they're in opposite directions, so I subtracted. You're exactly right. The total force on this third box would be 0 newtons. And so in this case, what was going on was the forces were balancing each other. Neither one of them was going to win. And in that case, since no force wins, we have no change in motion, which is kind of a big deal. So in the case of this third box, we say that the forces are balanced, which is very, very important. And I'll show you why. So as I said just a second ago, if the net force or total force is 0, then that means that the forces are balanced. And if the forces are balanced, the result of that is absolutely no change in motion. But that can mean 2 different things. The first possibility is that if the object you're talking about that the forces are balanced on is starting at rest, then if the forces stay balanced on it, it will stay at rest. There is no change in motion. If it starts at rest, it stays at rest. The other possibility is that if the object starts off in motion and then the forces are balanced on it, then it will continue that motion but at a constant speed. So if the forces are balanced, the object could either be at rest or traveling at constant speed. That's the important thing to remember. If the opposite is the case, or in other words, if the net force or the total force, whatever you want to call it, does not equal 0, then the forces are going to be unbalanced, which means the result of unbalanced forces has to be a change in motion. And if there's a change in motion, that means that the object is either going to speed up, slow down, or change direction. And where have you heard those 3 things before? That's right, you're thinking of it. It's acceleration. So, acceleration is caused by unbalanced forces. It all comes together. The last thing that we're going to talk about in this section of notes is something called inertia. And inertia is the tendency of an object to continue its previous motion. And that's kind of a weird definition for something to have, so I'm going to give you more of an example to help you think of inertia. But first, I want you to think about these few things I'm going to write. First thing that's important about inertia is that if an object has more mass, it has more inertia. So keep that in mind. Now, having said that, something else you need to know is that objects with large inertia are harder to start and harder to stop, which makes sense. If objects that have more mass have more inertia, then obviously huge, massive objects are going to be harder to start and harder to stop. These objects with large inertia are also easier to continue their motion. So it's easier to keep them going than it is something with small inertia. The opposite is also true for all of these statements. If you have less mass, you have less inertia. Objects with low inertia are easier to start and stop, and it's harder to continue their motion. So I'm going to leave you with this example. Think of a semi versus, we'll say something like a Camaro or a Corvette. Something very large, but versus something fairly small, but in the same category. First of all, the semi is going to have more inertia because it has more mass, obviously, a lot more mass. Now picture both vehicles. Which one is easier to stop? Which one's going to stop faster if you stomp on the brakes? Definitely that Camaro or Corvette, not that big rig. It's just not happening because it has more inertia. And that kind of goes along with the fact easier to continue the motion. So once that big rig keeps going, it's easier to keep it going. You don't have to put as much effort into it. With that sports car, it's going to take a lot more effort to keep that motion going. Same is true for something like a boulder versus a small pebble. Think of getting the boulder going versus getting the small rock going, and how easy it's going to be to keep that boulder moving once you get it, rather than having to continue to kick that small rock or small pebble to keep it going. So those are the things you need to think of when you think of inertia. And we're also going to have like a really cool example when we get back to class. So those are your section 2 notes. Make sure you copy them down.